Welcome to our lesson on creating an Excel calculator for handling a confidence interval for two proportions. As always, the full template is located in a link in the description. So let's get started with just the one we want to work with. Okay, as with all of our Excel calculators, the cells that are highlighted in yellow are the ones that we have to manually enter in the details from each new question we're trying to solve. The rest of these cells will auto-populate based on our new information. Okay, first thing, right? Group 1 probability of a success, and we know probability of a success is very simply just going to equal the number of successes divided by the sample size. Same thing for the proportion of group 2. It's going to equal the number of successes from group 2 divided by the sample size for group 2. Q1 and Q2 are simply the complements of P1 and P2, so that's easy, right? I mean, these are also P hat 1 and P hat 2. These things up here, I'm just not taking the time to put little hats on them. So equals 1 minus P1 equals 1 minus P2. This is simply the difference between the two, because oftentimes you need to know the difference between your two proportions. That's called the test statistic. Oftentimes it's referred to it as that. So equals P1 minus P2. So now we can see there's a little bit more than 6% difference between our two group proportions. Okay, our alpha, which is our error rate, which is just 1 minus our confidence level. So we put in the confidence level that we wanted 94%. We wanted to be 94% confident with our confidence interval. So alpha is just going to equal 1 minus that. And then the Z critical level, we've talked about this before in previous videos, that we're finding the cutoff on the Z score, on the Z distribution that has the critical, the confidence interval and half of alpha all below it, right? Because we're looking for that upper bound that captures everything except for that half of the alpha that's in the upper tail. So that's why it's going to equal the confidence level, the 94% that's in the middle in the confidence interval, plus half of the alpha that's down below in the lower tail. And then that gives us the total amount that's going to be below this Z-score that we're looking for. So that's going to equal our confidence level plus this amount divided by 2. And you can see that that gives us 97%, which means, makes sense, right? We got the 94% in the middle, and then our alpha is cut in half, and we have 3% below it and 3% above it. So the upper bound for that confidence interval is going to have 97% of the area below it, because it just has that half of alpha, that 3% above it. And that's what we need for the Z-score. Because when we do the Z-score formulas in Excel, they always want us to give them how much area is going to be below this Z-score that we're looking for. So to find the Z-score, we're just going to use the norm.inverse function. So you can see it asks for the probability, i.e. how much area is below it, and that's this one. And then comma, the mean and standard deviation, because we have the Z-score and we're living on the standardized normal curve. The mean is 0, standard deviation is 1. So that tells us that in order to have 97% of our area under the curve below us, we would have to have a Z-score of 1.88, which we know is correct, because we know the empirical rule tells us if we go 2 standard deviations in both directions, right, it goes 68, 95, and then the third one is 99.7. Well, 95 means 95 in between the two, 2.5 in each tail, right? So 2 standard deviations is going to give us 95 plus that 2.5, 97.5. We're a little bit less than 2 because we only want 97. So it's kind of like a quick check to make sure we didn't mess up our math. But in any case, that's the z-score that we need to put into this fun little formula here. So now all we have to do is recreate this formula. So it will equal the z of alpha over 2, so that's this thing that we just found, times the square root of all of this stuff, right? So the square root of p hat 1 times 1 minus p hat, which is just the same thing as q hat 1, right? Divided by n1, and we don't have to worry about any parentheses because order of operations with these fractions, it's all multiplication and division, right? So it'll multiply, then it'll divide by n plus 1, then it'll add the next thing, but when we put in the addition, it knows to first do the multiplication and division, so we can just do p2 times q2 divided by n2. And then close the parentheses because that's everything that's inside the square root. Hit enter, and there is our E, our margin of error. Then the last thing we need to do is calculate the actual confidence intervals, which is just, as you can see here in the equation, we're taking the difference in the two p's, this thing that we did right here, and we're subtracting this margin of error, and then we're adding the margin of error. So the lower bound, right, is just that thing minus e, so it's going to equal that difference minus our margin of error, and then the upper one is going to equal the difference plus our margin of error. And that's it. We now have an automated calculator that will give us the confidence interval for any question we have that involves two sample proportions. For instance, if we had the exact same thing, but they said now create a 99% confidence interval. Look what happens, 99%. See how the z-score gets much bigger? And then so does the margin of error, and our confidence interval gets wider. All right, thanks for watching.